Welcome you all to this Cryo-EM course. Last class I mentioned that today's class we will discuss little bit about the contrast transfer function. If we do not discuss about the contrast transfer function, it will be a bit difficult to understand what we are doing, how we are doing the data processing, because whenever you look at the data processing pipeline you can see that contrast transfer function term it is coming, and when you are evaluating our data, that okay, what kind of data we are getting, is it do we have a good signal, or can we use this data to achieve a high resolution, that time we have to do that CTF estimate to see how much signal we are getting. Based on that we have to consider, can we keep this data for the image processing or not. So let us start with the contrast transfer function. So what is that contrast transfer function? CTF. Contrast okay. So contrast transfer function will just so here when we are taking the images and calculating that contrast transfer function, basically we are calculating, we are estimating the contrast transfer function. So how basically that is working in our actual microscope? If you remember clearly, I already mentioned previously that okay, so when there is a electron beam, it is coming through that. If we just consider that is the condenser lens 1, and then this is the condenser lens 2, and electron beam will pass through the sample. Our sample is somewhere here, you just consider this is our C2, right, electron beam. That definitely I should make a parallel beam. I did not want to make it parallel beam. So in this particular case you have to make your electron beam, there will be a converging point in somewhere, and then electron beam should go like a parallel. So here I am just using it, so like that. So now there is the upper objective lens and lower objective lens which is helping to converge the electron beam in your back focal plane, and it will go all the way down to give us a image. So this is our back focal plane, okay. And back focal plane, if you remember correctly, what we are recording basically the diffraction pattern. So if you have a single slit experiment, if you remember those things, that how diffraction patterns are coming, and I already plotted those diffraction pattern, that okay, when there is a sine wave, one sine wave is going in this direction and we want to plot that one, how we can plot it? This will be the frequency, this will be the spatial frequency, or k I can tell, and this is the amplitude square. So based on the frequency you can get 1 here and you can get 1 here. And now how this sine wave is changing their path, or cosine, and this this vector position, it will change. The vector can go in this direction, and the intensity means amplitude square, based on that the height it will change. So what basically we are reading here? So in the diffraction pattern basically we are reading this bright spot. So in the central always that bright spot it will come, because from the single slit experiment we can know that whenever there is a some light it will go and interact. So at the center you will get this kind of peak and this kind of halos. So those things it will converge in the center, and then the diffraction dots you will collect it different position. So now here in this back focal plane we are collecting all this diffraction pattern, and then when you will go to image plane we will get the image of that object. Now in this particular stage we are going to focus here when we are talking about the CTF correction, okay. So we are only considering the sample area, sample insertion area, and the this back focal plane where we are getting, or you can consider that image plane, okay, that we are going to calculate. So you just consider for now this is, there is a sample, okay, sample, your sample is, so some kind of sample it is here, and whenever electron is moving passing through that sample, this is basically a wave we are considering, that a cloud it is passing. So there is a, I'll just use a different color or this green color, that okay, this is, you consider that wave it is going. So when the wave it is going, it will interact with the sample. If you remember previously we discussed that how it is interacting with the atom. So is there is a one electron, it can go close to the, if this is the nucleus, it can go to the very close to the nucleus and then back scattered, or it can, there is a electron molecule is electron is there, another electron directly hit, and then there will be some kind of spectrum, it will go and this electron will displace, and that is called the secondary electron. Now there will be a electron, so there are most of the time, if I just draw this one, let me draw that. So this is our nucleus, and if we just consider, this is one electron and this is one incoming electron. So most of the time there will be no deviation of this electron beam, but there will be some electron, it will be very close to this electron and then they will deviate. So this is unscattered electron beam, right? If we just consider, those are unscattered electron beam and this is a scattered electron beam. This is unscattered and this is a scattered electron beam. Here also similar incident is going to happen. So first let us draw the unscattered electron beam. So this will be the optical axis and your wave it will go and merge somewhere your image plane. Now if you consider, because of this scattering, there is a scattering and electrons can scatter at different angle. So here you can see, if you just consider, this is the electron straight way, this electron can also go in a straight way and then it is scattered. So it should go like that. So there is a scattering angle, some kind of scattering angle is there. Not only that, if you just consider this electron is coming here, if you just consider both of them, the total path length of this particular electron and total path length of this particular electron, it will be not same. This electron travels more than this particular electron. So path length wise, if you just consider, this is a one electron here, so electron 1 and this is electron, blue electron, and the path length if you just consider lambda wise, so lambda e, it will be smaller than lambda d because it has to travel more distance. So the scattered electron, there is a two changes are there, one is the angle and one is the path length. So in this particular case, when you will draw this diagram, we will consider that for now you consider all the scattering angle is same and then there is a path length difference. So if we just consider that, okay, there is a second wave, so second wave it is going like that and then it is coming and merging somewhere here. So this goes like that. So if you just consider that there is a scattering angle 90 degree and path length difference, if you just consider, for now you just assume that that is happening, and that will help you to understand that entire system. So if there is a 90 degree angle change and then if there is a path length difference between this red and this blue, if we just consider, it is lambda by 4. So you can see there is a total change, it will signal transfer when the all the entire signal it is coming and recording here unscattered and scattered electron, you can see there is a total path length change is almost 180 degree, right. So now if we want to plot those things in vector plot, that you know, if we in vector addition I showed you that okay, there is a one wave, so that should be the red wave, that is the unscattered electron, right. So that is coming in this direction, and then first one that there is a blue wave, there is a change in 90 degree, first there is a phase change will be 90 degree, and then because of the path length difference there will be another 90 degree change. So total, if you just consider, there is a total 180 degree change. Now if you plot this blue vector, you can see there is a difference. Now if we just, I told you that phase difference you keep it fixed, don't change this one. So I have another wave, so if I just consider that there is another wave, it is coming and it is merging here. So it is going all the way here, so if you just consider this angle is again 90 degree, and the path length, if you just consider, the path length is much higher. If you just consider this blue and the green one, the path length of this green one is much higher than the blue one, right. So in this particular case, we can consider that it is path length difference is lambda by 2. If we just consider that lambda by 2, what will come? It is 180. So it will come total 270. Total change between this blue wave and the green wave. Now if we want to plot that one, that blue wave and green wave, so the unscattered electron beam is as it is, there is no change, and now it is coming first 90 degree change in the green, and then again 180 degree change. So wave is coming here. So now if you do the wave addition here, what you will get, the resultant wave, you will get this one, right. So now here, so addition of this two particular wave, then blue wave with the green wave. First we are adding red and the blue wave. So wave number, so if I just use the red color, wave number 1, then wave number 2, wave number 3, and now we'll keep going on like that. So then wave number 4, if you just start calculating this, is only 2 waves are there, and then we are trying to plot entire thing. What we will get it at the beginning, it is, you can see when we are starting at 0, the first one, it is in between this blue wave and the red wave. So that is our the wave number 1 and wave number 1 and wave number 2. So this difference, you can see actual amplitude, we should get this red one, and that amplitude should be here. But when there is a other wave, that blue wave thus interacted with our red wave, and we are losing the amplitude, our resultant wave is much smaller than actual one. So in electron microscope is also happening same thing, because billions of electrons are coming together and they are interacting. There will be some has had a completely different phase, their amplitude is reduced. So in this particular case, if I want to plot this one, you can see I am plotting this one in the negative direction, because this blue and red wave together, so this blue and red wave together, it is giving me a signal at the lower amplitude. Now if I consider the next one, that is, I showed you this one, which one is the blue wave and the green wave. So this is the unscattered electron beam, and then if I just consider what is the change between this unscattered electron and the scattered electron with the green one, what kind of change is there? Change is initially 90 degree and then another 180 degree. So total 270 degree. If we just plot this 270 degree, that means the amplitude, there is a not too much change. So whatever we have, this information unscattered and scattered electron is almost giving the same information. So there are not too much change between these two waves. So if I want to plot that one, you can, for the green wave you can get something like that. If I just consider that unscattered electron started from here, that is the red one here, so that is the center, that is the 0, so there is no increase, nothing. So unscattered electron is here, then there is a scattering, and between the scattered and unscattered we are getting something less amplitude. Then the next wave, when we are calculating, we are getting something almost 0. So there are some information, but due to this scattering interacting between the multiple waves together, those informations are lost. Means there is not too much amplitude change, that is almost same like my unscattered electron beam. Now similar way, if I just go to the next one, that okay, there is a change, right? So if I just consider that okay, third one is that red one I want to calculate. So there may be that okay, there is a 90 degree shift, and I can tell that in the next step it will be, if you just consider that there will be 3 lambda by 4, the path length change. If we just consider this red one, the scattered red one and unscattered red one, that means wave 4. So what is the path length difference? Path length difference is that. So this is the wave 4 path length difference. Path length difference, and this is the scattering angle. Now if you just add them together, what you will get it? So you will get it 360-degree change. Now if I want to plot that 360-degree change, so what I have here, this is my unscattered electron beam, that is my wave 1. Now there is a 90-degree change, my scattered electron. Then there is a again 270-degree change. So this is my 90-degree and then even 270-degree change. Now you can see this wave 4, basically this wave 4 and wave 1, if I want to plot them here, what you will get the much higher amplitude here. So we will get it like that. Now here I am just showing you two waves. So here multiple waves can come and then they can interact, and similar way you can get all these values here, how we are plotting, and you can see that is again a sine wave it is going. So something like that, right? And more wave can come, more and more wave can, scattered electron can come, and we can add them. So you can see, what if we just consider one single wave, we can consider that okay, there is no other information, it is a sine or cosine curve. But after interacting with multiple waves together, after scattered and unscattered electron, if we just start adding them, we are getting this similar kind of function, similar kind of wave again, and that is a combination of multiple waves together. So this is how, when you are recording an image, we are transferring the contrast. So this is basically how you are transferring the contrast, where multiple waves are interacting together, and that is recording in your image plane. So this is not a single wave or single sine, this is a combination of multiple waves together. So that is called the contrast transfer. How the contrast is transferred from the sample to your image. When this contrast transfer function, so there is some kind of function, right? How do we mathematically represent that? CTF, if we want to tell, it will be sine minus pi delta z lambda k square plus pi again, then CS and lambda 3 k4, k to the power 4, yeah. So it will be half of that, half we can just consider that, okay. So in this particular case, what we are here, this is a very complicated function, we are not going into the mathematical details. Here there is a two things are important, one is this and one is this. So CS, basically the spherical aberration, we all know that, that is called the CS, and the delta Z is playing a very important role, that is called the defocus, okay. So defocus value is regulating this CTF. Here we are estimating the CTF. What is the CTF here? What is the contrast transferred in the image? So we are basically plotting that amplitude square, and this amplitude square is going to affect when the multiple waves are scattered with each other, and then there will be some cases that some information will represent in a negative direction. If we just consider, this is the amplitude and this is the frequency. So some amplitude is represented in a negative direction, some it will be in a positive. So if we just plus and minus, so it is because of that scattering, all this event is happening. all this positive, negative, this change is happening because of this scattering of multiple waves. So here also you can see there is a positive and negative, this change is there, and this are going to record where this represent that addition of multiple sine waves, because that is we are when you are having a image and we are going to in Fourier space or in diffraction pattern, we are basically doing the inverse Fourier transform of this image and we are getting those dots, and those dots means if you just consider the diffraction pattern means multiple waves are coming together and merge together and giving that dots. And if we can just split one by one sine wave, that is called the Fourier decomposition. Okay. So we are not going to that direction. So this is our contrast transfer and we estimated that, and that is depending on the z, and delta z means the defocus value. How this defocus value is connected, if you just recall our previous discussion. So when we have a sample, when all the image it will come and form in particular one, if it will converge here, that is called the focus. Okay, here again that is called under focus. That is called over focused. So in cryo-EM most of the time we are using this under focused sample, because most of the data processing tool considering these under focused images and calculate that delta z value, and that is helping us to go for the 3D reconstruction. Most of the time we don't use the over focused image. When you have something in a very particular focus, you cannot see the image properly. That I already discussed, I already showed you that how this focus value we are changing and we can get a different kind of white fringe or black fringe, and that will isolate our particle from the background, and that will help us to distinguish the sample from the background. And our sample is mostly carbon, hydrogen, nitrogen, oxygen, scattering is very low. So if we use some kind of defocus value, either under focused or over focused image, that will help us to visualize the sample, that we already discussed previously. So here you just remember that we generally don't use the over focused image, mostly we use the under focused image, and this under focused image, all the software what we are using for the image processing, they are considering your images are collected at the under focused image. This under focused value we are calling then defocus value. This defocus value is represented by delta z. So you can see that CTF curve is directly connected with this defocus value, if you remember the mathematical problem. Now this defocus value, how it is affecting, if we just consider that okay, this is your optical axis and going. So if this is the sample, after interacting it can converge here, or it can converge here, or it can converge here, or it can convert somewhere here. So here you can see those all are different defocus value. Delta z it is changing. So we are using different kind of minus delta z value which is changing their converging point or imaging. So in those particular case, delta z also going to affect your CTF. Why not? If you just consider where your image wave is coming and merging, in this particular case, in this particular delta z value, your wave is merging here, but when the wave is merging somewhere here or somewhere here, it has to travel more, path length it is going to change, and that is going to affect how they are transferring the contrast, and that is we are recording. So this is how the delta z is directly connected with the contrast transfer. Okay, how this contrast transfer is happening there? If we just consider that how this contrast transfer function is playing an important role. So here you can see I will just first draw this contrast transfer. So, this is our contrast transfer. We are always assuming when all these waves are converged in particular, some point we will get this negative contrast, some point we will get the positive contrast, and so on, and it will be in uniform all the time. All the time we will get a something very high amplitude and sometime a negative amplitude. So, in this particular case you have to remember, when even there is a negative amplitude, that is also coming from your scattered and unscattered electron beam, that is also a signal, but we plotted in a negative, and here this one is the positive. So, somehow we have to flip that signal back. Before going to that, first let us take a look what is the connection with the defocus value. So, in this particular case, even if you just look at the power spectrum, what you have at the central, you have a white, very bright. So, multiple dots are basically presented here, all this amplitude, and those things, if we remember properly, I always say those are basically the low frequency signal is stored here. All the low frequency signal is connected here. Now, if we go for a high frequency signal it will, so here all the low frequency signals are stored here. So, low scattering. So, when there is a scattering, this is an unscattered electron beam, right? Then there will be another scattering, So, whatever is the low scattered electron, all are stored here. So, where there is a very strong scattered electron beam, they will stay far away from the center. So, that also from the diffraction pattern we all know that. So, the scattering angle, it will scatter smooth. So, those are basically our high frequency signal when they are stay away from the central part, if this is our the entire image. So, the center part only the low frequency signal will store, and high frequency signal. So, if you just remember this one, when there is a wave like that, this wave it is going, and we want to plot that one. We know that frequency is 1, so we are plotting this one. Now, if there is a wave like that, frequency is, if you just consider frequency is 4 or 5, and we want to plot. So, the high frequency signal now. So, those high frequency signal you are plotting it far away. So, here also those are the high frequency signal. Now, every signal when it is transferred, it will transfer like this sine wave or cosine wave, whatever it is. Now, here if we just replicate the same thing here, this called the low frequency signal, this called the high frequency signal. Okay. When we are using the different kind of defocus value, what is going to happen at different defocus value, when we are using the delta z value very high defocus, your the signal it will start going down. Why I am reducing this signal like that? This is called the envelope function. I am going to talk about that. Here you can see all the amplitudes are same, but that is not possible in real scenario, because if you go far, if I am talking about this is the high frequency signal, so low frequency signal your amplitude will be good enough, but if you go far away from your center part, your signal will go down, your intensity will be low, your amplitude will be low. That is the reason it cannot be fixed amplitude like that. So, that is called the envelope function. So, why this envelope function it is coming, we will discuss in the next class, but in the meantime you will just look at. So, when you are using a very high defocus, this signal it will boost in this particular direction, and you cannot, so initially you can see that your signal should come until here, and just because of very high defocus value, this low frequency signal is very good. The low frequency signal will be dominate. So, this low frequency signal will be dominating. So that will help you to see the molecule properly, see the molecules properly, because you can get, if this is your particle, outside you will get a very thick fringe outside of this molecule because of this high defocus value. That will help you to visualize the particle, but you are going to lose the high frequency signal. That is the one of the drawback, right? Now if we just consider that, okay, what will happen if we have a very low defocus value? So if we have a very low defocus value, your wavelet will go like that, like that. So your amplitude will be not very high, it will be not similar. This is, you can consider that low defocus value, delta Z value. So your amplitude will be not very high and it will go until end, until Nyquist, and cover most of the signal. Whatever signal you have, you can restore. It is not going like that, you don't have any signal in this particular region. So in this particular case, when you have a very low defocus, your amplitude will be low and it will go until Nyquist. In this particular case, you cannot see your molecules properly, maybe because of the low defocus value, your this outside fringe will be not that great. So here, if this is the molecule, maybe it will be only one very light ring, it will come. It will be not prominent like this at low defocus value, but you can restore your signal until the end, until the Nyquist. So this is the connection between the high defocus and low defocus. So you can consider that if you use a very high defocus value, it will good for your eye, you can see the sample properly, but it is, you are losing high frequency signal, means you are losing all this high frequency signal. So you cannot get a high resolution structure because you are limiting your signal, something like that. But if you go for a very low defocus, that is not good for our eye, we cannot see the sample properly, but you can restore all this high frequency signal when you have a very low defocus. So I hope now it is clear how it is transferring the signal and what is the relationship between defocus value. We can discuss more about these things, but this is not the actual platform or course where we can discuss more about how those are connected with the CTF and what kind of transfer it is happening and rest of the part. Here I am just giving you a brief outline how if you suddenly see in the pipeline there is a CTF, what is called the CTF, what we are correcting there. So that is the reason I discuss these things in future. If we take another course where we are going to discuss more about this CTF and how it is going to affect our images and what kind of corrections we are doing. In the next class, we will talk little bit about the envelope function and we will directly go for the 3D reconstruction part. Thank you all for your attention.